Okay, so in this section, I want to go over just a little bit more in depth on how we actually make the molecular formulas correct when we're making ionic compounds. So I'm just going to write down a couple of compounds, and we're going to use iron as our first example. So if I say we want to have iron chloride, okay, so if I just name this, we know that iron can take a couple of different oxidation states. So if I don't tell you which form it's in, we know it can take one of two states. Iron can be an iron 2, so we could have the option of making this 2 here, or iron could be in the iron 3 state, so it can also take an oxidation state of 3 because it's in the transition metals. And in fact, let's just take a look at iron first before we write out the formula for iron chloride. And let's just review the electron configuration for iron, and we'll show why it can take these two different oxidation states. So if we look at iron here, we can see iron has 26 electrons. It's in the D block, and we know our D block is at the N-1. And so the N number for this one is 4. So this is the third D block, so 4 minus 1. So this is the 3D block, and we know that this is 3D1, 2, 3, 4, 5, 6. So iron is going to end in 3D6 for its electron configuration. Okay, so iron electron configuration is going to end in 3D6. So if we walk it back, so this is where it's going to be filled, we would have to fill 4s2. The next one going back is 3p6, and then 3s2, and then the 2p6, 2s2, and the 1s2. So 2p6, 2s2, and 1s2. And we can double check our electron configuration, so we know that iron contains 26 protons or 26 electrons in its elemental state. We can add these up real quickly, make sure they match. We've got 10, 18, 19, 26. So those add up to 26, so we know our electron configuration is correct. And we know that the valence shell for iron is the 4s2, right? This is the highest shell level that we have available. And we know that there's 2 electrons in there. So it makes sense that it can lose those 2 electrons and that iron can take the 2+ state when it becomes a cation. But we also know that iron can take the 3+ state. And it does this because of these d orbitals. So if we think about how the electrons are filling these different orbitals, we know that our 4s2 has 1 orbital, and it contains those 2 electrons in there. So we could write this guy out just like that. And then this 3d shell that's here, the d subshell has how many orbitals in there? Do you remember? Hopefully you said 5. So our d subshells contain 5 orbitals. So we could write those out, and they're going to fill singly first. So we'll have 1 electron here, 1 electron here, 3, 4, 5, and so they'll fill separately first, and then that 6th electron has to start pairing up. And so there is actually greater stability if these guys can all just live as single members within the d subshell. So it's this electron that's paired up in the d subshell that is not as stable. And so this actually has a little bit higher energy. It's pretty close to the energy of the 4s subshell. And so this guy can come off too. So the 2 electrons in the valence shell from the s orbital can come off and form this state, or all 3 of these can be lost. If all 3 of these are lost, you can get this state up here. So you're either going to get just the 4s2 and the 2+ state, or that paired one in the 3d subshell can also come off and give you iron 3+. So now that we've reviewed this, let's go ahead and build our iron compounds. So if we were going to build iron 2 chloride, we would start, I always start building compounds by just putting one of each element into the compound, and then I evaluate the charge on there. So if we just put one of each, we could say we've got one iron and one chlorine. And we want to make iron 2 chloride first. So the first thing we need to evaluate is what is the charge on the chlorine. So let's do iron 2 chloride first. And so what I like to do is to just put down one atom of each element first and then evaluate the charges and see if it's neutral or not. So I've got one iron and one chlorine so far. And so what I kind of like to do when I'm starting to do this is I like to draw a box on top of my molecule, and in one of the columns, and so I'll have one for the iron and one for the chlorine, and then one where I'll do the summation kind of out here. And so in this first box I'm going to keep the charge, and then in the second box I'm going to put the number of atoms, and then up on the top I'm going to have the total. This is where we really start evaluating now what our charges are going to be. From the name, I know I've got iron 2 in this first one if we're going to make iron 2 chloride. So I already know the charge on the iron. The charge is going to be 2. I don't know how many atoms are going to be there yet, so I'm going to leave that blank. And then we can look on our periodic table for chlorine. We know chlorine is over here, and that it's in group 7, so that means how many electrons is it going to need to complete its valence shell? Hopefully you said 1, so it only needs 1 electron, so it can only gain 1 electron. So it's going to have, the iron is going to lose 2 electrons, but the chlorine can only gain 1 electron. So you can see here, if we only had 1 atom of each, this is not going to balance the charge, right? There's going to be a +1 charge on the overall molecule. So if we just have 1 of each, we still would have a +1, and this is no good. So the overall charge needs to be 0, right? We want to get this one to equal 0 up here. So this is where we can do our cross multiplication when it comes to how many atoms that we have. And so there's 1 on the charge over here, so we're going to have 1 atom of iron. With the 2 charge over here, we're going to put that in our number of atoms up here. If we have that number of atoms up here, we have to indicate that with the subscripts on our formula. So remember, the subscripts are going to indicate the number of atoms. So if we're looking at the total charge then, we're going to say a +2 times 1 is +2, and a -1 times 2 is going to be a -2. So when we add these two together, that's going to equal our 0. And so this is going to be a balanced formula. The overall charge on that formula is 0. So if we have the similar situation, if we have iron 3, so if we are making iron 3 chloride, how many atoms of iron are we going to need, and how many atoms of chlorine are we going to need? Our charges are going to be a little different. The chlorine will remain the same, -1, but our iron now is going to lose the 3 electrons and be in the +3 state. So if we draw our charge box on the top again, what we see is that we've got a +3, a -1, and we do the same cross multiplication again. So we're going to have 1 atom, and then we're going to have 3 atoms of the chlorine. So again, we've got to show that as the subscript. We've got to put the 3 down here in this case. We do the summation, we'll have a +3, and this one will be a -3, and overall the charge is going to be neutral, or the charge is going to be 0. And so this is a good way to figure out the molecular formula for your compounds. Again, this is also why it's very important to also show the Roman numeral in the naming. Remember, our Roman numerals indicate the charge. Okay, so they don't indicate how many atoms are present, they're indicating the charge state. So let's try one more. So let's pick one that's maybe a little bit more difficult. So let's pick aluminum oxide. So we know that aluminum, if we look at our periodic table again, so this is in group 3, 1, 2, 3. So our aluminum is a metal and it's in group 3. That means it's going to take the +3 state. So it should have a charge of +3. And our oxide is the anion is going to be oxygen. It's in group 6, so the charge on this guy should be -2. So this one we can figure out the charge state very easily. So if we're going to put them together in a molecule, again, we want to start out by just writing one atom of each and then using our charge table to determine how many atoms we're going to need of each one. So right now we've got one of each. Let's draw our table up here. So this one again is charge, and this one is number of atoms, and then we'll put the total up at the top. So for the aluminum, we already said the charge is +3, and the charge on the oxygen is -2. So we can already see if we only have one of these, this would be the base charge state, and so we would still have a +1 charge on the molecule. That would not be correct. So what we do is the cross multiplication rule still works again. So we're going to put a 2 up in this number of atoms, and we're going to put a 3 up in this box for the number of atoms of oxygen. These guys, the number of atoms, again, equal these subscripts in the formula. So we've got to put them down here. So for the aluminum, that's going to be 2 aluminum atoms and 3 oxygen atoms. So these have to come together. And then we can do our multiplication to check. So if we've got a +3 charge on each atom, we're going to have a total of +6 on the positive side. And then if we have a -2 charge and we have 3 atoms of these, we're going to have a total of -6 on the negative charge. And so +6 -6, that's going to equal 0 overall. So our overall molecule is going to be neutral. So we know that this is the correct formula for aluminum oxide. All right, so that's just a couple of examples. If we do one that has a polyatomic ion in it, let's do one of those as well, just to give you a little experience with that. Let's do calcium phosphate, because that one's kind of a hard one. Okay, so phosphate is the group that you would look up on your polyatomic ion chart. You would be given this on the exam, so you don't have to remember what your polyatomic ions are. And if we look this up on the chart, we would see that the formula for phosphate is PO4, and there is a -3 charge on that molecule, so it's got a -3 charge. Calcium we have to figure out using our periodic table. So we come back over here and we say, where is calcium? So we can see calcium is here, and so it is in group 2. So these guys are going to lose the 2 electrons to become cations. So calcium should be a +2 charge. So we know calcium should take a +2 state. So if we're going to make our calcium phosphate molecule and get it to balance out so that it's neutrally charged, we'll start by putting one of each of these together, and then we'll work through our table to find out how many subscripts we're going to need. So we will have 1 atom of calcium and 1 molecule of the phosphate, and I'm leaving a little bit of room to put some subscripts in there. So now we're going to draw our charge diagram on top. So we've got again the charge, we've got the number of atoms, and then we'll have the total on the top. So our calcium we said is +2. The phosphate based on our table is -3 for its charge state. And again, we can see if we only have one of each, this is still going to give us a -1 charge on the molecule. So that molecule would not be happy. The molecule, again, needs to be neutral to be stable and remain in the environment. So again, we can use our cross multiplication rules. And we can say since there's a 3 over here, I'm going to try putting 3 atoms of calcium there. And since there's a +2 over here, we'll try putting 2 molecules of the phosphate group together. So we need to put these guys, are going to again equal the subscripts. So the calcium's easy, we just put the 3 down there. And now with the phosphate, we actually have to use parentheses around the phosphate. So to indicate that there's 2 entire phosphate groups that are going to be present in that molecule. If you just wrote it like this, what this says is that I have 42 oxygens and 1 phosphorus that's going to be present there. So without having the parentheses here, the parentheses here indicate that I actually have 2 physical phosphate groups. So if you were actually looking at this in more of a 3-dimensional or a structural way, what you would see is that this molecule would look more like you would have the phosphate groups, and you might have another one sitting over here, and then these would be toggling with the calcium groups. So we've got 2 of the phosphates, right, and they have -3 charges, and so they're going to be maybe toggling like this with the calcium. Calcium's got a +2, so it can interact one with this, and then there's going to be another calcium over here interacting with its 2 charges over here, and another calcium interacting over here. So a full molecule of this guy would be built around the charges of the phosphate and the calcium, where the calcium is going to want to be next to the phosphates because this is positive, these guys are negative, and again the calcium is going to be linked to the phosphate group. So that's indicated then by this molecular formula, and so this is the correct formula for our calcium phosphate. Alright, hopefully that gives you a little bit of review in creating your ionic compounds and getting the correct molecular formulas.